fermionic bosonic property. Applies to the entire wave function. And if, you know, the spin is not coupled to the spatial part, then the total wave function is usually something like there's a spin part and then a spatial part, which, you know, would include the coordinates. So it'd just be a product of the two. So you have to make sure that, you know, that product is the thing that's even or odd under particle exchange. So that should help you with the quiz, which you should take. There's a quiz. So that's one of the questions on the quiz, just very important. You recognize that when we talk about identical particles, it's the entire wave function. It has to be symmetric or anti-symmetric, which leads to these possibilities of having the different components of the wave function, like the spin part or the spatial part, have be either even or odd, because it's only the product that has to satisfy the fermionic or bosonic property. Okay, any questions, comments? This identical particle stuff is relatively conceptual, so it's nice to discuss it a little bit as opposed to doing specific calculations. We'll get to calculations in a bit, but okay. Well, we also talked about scattering a little bit. And the idea there was if you have, for instance, spinless bosons, so you think about spin zero particles, which have just a single state for the spin. You don't have to worry about the spin, you're just worrying about the spatial part. Well, if you scatter two of these things, then if they're identical, there's no way to tell which one scatters in which direction. So there's two kinds of processes that occur, and they're indistinguishable, meaning that they have to add constructively in terms of your quantum mechanical probability amplitude. One option is that the two particles come in and scatter this way, where this guy just turns around and heads into a detector up here, and this guy turns around and heads into this detector down here. And the other possibility is that, and this, if you think about what the scattering amplitude would be, say for this guy, it has incoming here and then it's outgoing here. So there's some angle, you know, theta associated with the scattering amplitude. Or better yet, maybe the way we did it. So you can think about the other possible process, which is that the particles exchange roles, and it's this one, the one on the left that goes into the upper detector, and the one on the right goes into the lower detector. But these processes are indistinguishable. But if we think about it in terms of scattering amplitudes, like for this process, then of course, in this case, you're sort of incoming in this direction and you're outgoing at some angle theta away from the x direction. So there would be an associated scattering amplitude of f theta. But of course, this guy right here, you would have this angle instead for the other process, and this angle, the relationship to theta is that it's just pi minus theta. So there'd be a scattering amplitude associated with going in this other direction, which would be pi minus theta, because that's that angle, and that would be the angle between the incoming particle and the outgoing one. And so the idea is that those two, if you have spinless bosons, you don't have to worry about the spin states of your particles that you're scattering. So you only worry about just a single amplitude, just the scattering amplitude. Then those two scattering processes have to interfere. So that means that there's a total scattering amplitude, which is just given by the sum of the two scattering amplitudes. And we know that we have to add them with a plus sign, because if we think about what happens under particle exchange, right, the two processes interchange. So if we exchange the two particles, then f theta becomes f pi minus theta, right? This is exactly what happens under particle exchange. You transition between these two kinds of processes. And so if you have spinless bosons, then you better make sure that your wave function, the scattering wave function, is symmetric under particle exchange. And that's precisely what this tells you, right? If this is what you interconvert between these two under particle exchange, then your total scattering amplitude is going to be symmetric under particle exchange, because all particle exchange does is it just flips that angle from theta to pi minus theta. All right, so that's bosons. That's sort of what we left off with last time. Any questions? All right. Well, you could also have, of course, fermions. For instance, you can have spin 1/2 particles. Well, in that case, the situation's a little more complicated, right? Because, well, you could send in different states of the particles, and they could scatter, and they might scatter into different states, either spin up or down. So each particle is, the spin states form a two-dimensional Hilbert space. Because, there's a spin state now that you have to consider, and you have to think about how the spin might change under the scattering. So, so basically what will happen is that your scattering amplitude is no longer just a simple number, like a complex number. It has to be what? What does f have to be instead of just a number? Any guesses?
A vector?
Close. Even bigger than that. Yeah, it's got to be a matrix. So what's the size of the matrix?
Would it be 2 by 2?
Nope, a little bigger than that.
4 by 4. So
Yeah. It should be a 4 by 4. Because, why is that? Well, because the scattering amplitude describes what happens. It describes the connection between the incoming stuff and the outgoing stuff, right? So you need four-dimensional, you need four different possibilities for both things, right? So there's four combinations of incoming states. So you need to do like up, 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 down, 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 up. And then there's four possible states that come out, right? Either up, up, all the four spin combinations. So indeed, it has to be a 4x4 matrix because that covers all the possibilities for scattering, right? You have all the four different ways of coming in and the four different ways of coming out. And so there's a scattering amplitude associated with each of those different combinations for a total of 16 different possibilities. It might be kind of surprising that already at spin 1/2 you have so many possibilities, but it's true if you think about it. There's just lots of different ways that you can send spins in and have them come out, right? You could probably, you can enumerate them if you want, up, up to up, 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 up to down, down, up to down, up to up, down, all those. So it's 4x4 matrix. But we do know something. We know that the total angular momentum during this process should be conserved, which means that if the two spins are originally, have some angular momentum, then that angular momentum should remain the same after the scattering. And so that means that during the collision, if the spins are in a singlet state, then they should remain in the singlet state. If they're in a triplet state, then they should remain in a triplet state. So, although in general, be a 4x4 matrix, it's actually quite constrained. The conservation of angular momentum tells you that there's actually only two possibilities, or there's two terms, if you wish, because not only do you have conservation of angular momentum, but you also have that these particles are fermions. So they're also identical fermions. So remember what that means. That means that the total wave function has to be anti-symmetric under particle exchange. So how would you concoct that? Well, that means that this guy must be the following. It must be some scattering amplitude associated with the singlet. Remember, when you're in a singlet state, that's an anti-symmetric spin state. So the spatial part of your wave function, which would include the scattering wave function, has to be symmetric. And so this would be the amplitude of the spatial part of the scattering amplitude. And this would be multiplied by what? By the matrix associated with the projection onto the spin singlet space. So this is the projection operator onto the spin singlet. Remember, this is now the projection operator in the tensor product space of the two electrons, which is a four-dimensional space. So it's a projector, so it's a matrix living in the four-dimensional two-spin tensor product space. And so it's 4x4 matrix, just describing the projection onto the spin singlet state. So this is a but that's, of course, not the only possibility. The other possibility is that the particles are in the triplet state. So the other possibility is that you have a scattering amplitude associated with the triplet state. In that case, the triplet spin state is symmetric. So the spatial part has to be antisymmetric to make the whole thing antisymmetric. And this would be multiplied by the 4x4 matrix corresponding to the projection onto the triplet state. Or, the triplet has three, it's, there's a single spin singlet, because that's spin 0. And of course, there's 3 states corresponding to the triplet state. So it's a projection onto the space, onto the portion of your Hilbert space that corresponds to the spin triplet states. And you can construct these explicitly by just, writing out the projection operators. Essentially, this would be the projection operator onto the spin singlet, which is, up, down, minus, down, up. So you take the bra and ket of that and, construct the projector. This guy would be everything else. So you could think of it as the identity minus the spin singlet projector. And those are 2 possibilities. And then this always works out that any situation you can think of is either going to correspond to one or the other. And well, there you go. And this is constructed in such a way to make the idea of preserving the fermionic character of the wave function work out. And so what would you do? How would you use this? Well, you would use it in principle. You would prepare your scattering with some spin states, that you're sending in. And so you would then have an associated differential scattering cross-section for 2 initial spin polarization states, like up, up, or down, down, whatever you want. So you would have some states, Pi and Pj, your initial spin states. And for each of the possible and really, I guess, so you should really, maybe a better way to write this is, so, okay, you have your initial and final spin states, and that would consist of specifying the spins for both particles as you send them in. So there would be a P initial. These are the initial spin states for the 2 particles, and then you would have some final spin states. And then you would have a differential scattering cross-section for each of the possibilities for the incoming and outgoing states. So again, there would be 16 of those combinations. But if you pick some specific ones, if you're looking at a specific channel, as they say, like say you're looking at the up-up to up-up channel, then how would you calculate that? Well, you would just take that final and initial state of interest and sandwich it with your scattering amplitude matrix here. And just take the square, and that's how you would do it. That's how you would find the differential scattering cross-section associated with that particular channel. That's if you know exactly what the spin states are of the incoming and outgoing particles. But oftentimes when you're doing an experiment, the incoming particles you're sending in, you don't know what their spin states are. You often just send in some beam or something like that, where you don't polarize the particles in it. You're sending 2 beams of electrons or something at each other, so you don't know what the initial polarizations are. And in that case, if you don't know which ones, and if you don't care what the final polarization is, right? Maybe we're just detecting ticks in a detector, like clicks, right? Either the electron hits the detector or doesn't. We don't care what spin it has. Well, in that case, if the initial spins, and this is the typical case, unpolarized, and we don't care about the final state, then of course you just get the differential scattering cross section, which would be a sum over all the possible initial and final states of the two spins. And you would have some probability of being in a particular initial polarization. And, you know, this probability could be, if it's polarized, you could, you know, concoct the probability to pick out a particular initial state if you want. But typically this will be sort of equally distributed among all the different possibilities, the 4 possibilities. And of course, for each one of those, you would calculate the following, right? You would calculate the square of the scattering amplitude matrix. And of course, and where we sum over the possible final states. And this is just the complex conjugate. So, and what happens here? Well, you see in here, we have a completeness because we're summing over all the possible final states. So this is just a completeness relation. So all this is a sum over the initial polarizations, probability of observing a particular one, and then it's just the product of these two scattering amplitude matrices, which we can also write as the trace of, remember that this is just the trace of the state operator multiplied by f hat dagger f hat. Remember that the density operator generalizes this idea of if we don't know what particular ket we're in, then the state operator, remember, is defined as the sum over all the different kinds of states that you have of the probability of observing that particular state times the projection onto that state. Remember from last semester, important concept when we were dealing with adding classical uncertainty. If we don't know which particular ket we're in. And that's what would happen if you have an unpolarized beam. We wouldn't know which particular ket we're in. And so for a truly unpolarized beam of incoming particles, you would have that the probability of observing any particular polarization, you know, up, up, down, down, you know, your basis is just going to be a quarter, you know, because there's 4 possibilities, right? The up, up, down, down, up, down, down, up. So we can actually calculate now the unpolarized scattering cross section for 2 spin 1/2s, or 2 electrons, because we know everything about it. So what would it be? Well, it's easy because the state operator in this case is just going to be a quarter times the identity, right? 4x4 matrix of 1, so the trace of row has to be 1, right? Probabilities sum up to 1. So this is just a quarter of the trace of f dagger f. But we know what that is as well. So we can go back to our expression for the matrix, the scattering amplitude matrix. And we could plug in. Oh, sorry, I'm missing a dagger here and some hats. So we can plug in, right? So what would we get? We would get a quarter trace of the singlet amplitude star. And we're just gonna call this the total. I'm not gonna put in those minus signs. So this is FS total. This is FT total. Just to avoid having so many terms. So we have that's the total singlet star because of the Hermitian conjugate. We've got the projection onto the singlet state. Remember, if you dagger a projector, you get back out the projector because it just flips the Bros-and-Ketz, which doesn't do anything. Then you have the triplet part, again, the total star projector onto the triplet. That's the dagger portion. And the undaggered part is, of course, this. Okay, very nice. So now we can multiply this out. And moreover, we know these are projectors and that these are orthogonal spaces, right? You can't, right? They break up your 4-dimensional Hilbert space into 2 orthogonal spaces. One's for the singlet, one's for the triplet. So if you take the product of the 2 projectors, it just gives you 0. So it's only the projectors squared that matter. And if you square a projector, you just get back out the projector. So if you multiply this out, this f hat dagger times f hat, well, the only terms that contribute are just the diagonal terms. So it's fs total star times fs total. And then this would normally be the projector squared, but that's just the projector again. That doesn't, right? If you square a projector, you get back out the projector. Or by definition, if you keep projecting into the space, you're still projecting into the space. So you just get that. And this is easy to calculate also because the trace will just give you the dimension of that subspace, right? So the trace of this guy, spin singlet, there's only one state corresponding to that. So the spin singlet projector is literally just, this guy, projection onto the spin singlet. And, the trace is invariant under change of basis. So you could use that basis with the singlet in it. And so that'll just give you a matrix that looks like this, right? It'd be 1 and then a bunch of zeros, right? Everywhere else. So this just becomes the amplitude squared, as the trace is 1. And then you have the projector onto the triplet, but there's 3 of those states. So that would look like 0 and then 1s, right? That's for the triplet, where these are the 3 triplet states: the up, up, down, down, and the symmetric combination of up, down. So this would be 3/4 triplet. And now if we restore the actual amplitudes, it's kind of interesting. So you get that. And what's especially kind of curious, of course, is that, well, if you think about like scattering 2 electrons or something, they'll scatter via, the Coulomb interaction. They have the same charge, so they'll repel each other with the Coulomb potential. And the nature of the Coulomb interaction won't really depend on which particular spin states they're in, right? It doesn't really care about that. It just cares about their charge. So in a situation like that, there really wouldn't be any difference between the singlet amplitude and the triplet amplitude, right? It wouldn't really depend on the spin states. So typically for like Coulomb scattering, you would have these amplitudes are the same, because they only depend on the details of the Coulomb potential. And in that case, you can actually continue with this calculation, right? You can set these guys equal, so you can drop the subscript. And then for the unpolarized cross-section, what do you get? Well, we can start multiplying out all these terms, right? You'll get the diagonal terms, which look like this. You get the cross terms now from the spin singlet part. And so that's for the spin singlet part. Then you get the triplet terms, which come in as 3/4. But otherwise, this is the same here. And minus 3/4, the cross term. No, sorry. Of course, the star has to be on this guy. All right. So if we look at this, then clearly the diagonal terms combine. So you get f theta squared plus f pi minus theta squared. And remember, this part would be what you would get for scattering 2 distinguishable particles, right? That would just be, if you don't care which one went in which detector, that would be what it is. You just sum up the probabilities of the 2 different kinds of processes of scattering. But in this case, we have an interference term. And if we look at what happens here, this is 1/4 minus 3/4 of the same term. So this would be a total of minus 2/4, which is minus 1/2. Be minus 1/2 times this. And if you look at this, this is just twice the real part of f star theta f pi minus theta, right? Because if you add that to its complex conjugate, that's the real part. And that's kind of interesting. This is the interference term that you would get due to the identical nature of the particles. And you see it'll be of opposite sign and also half of what you would get for like spinless bosons, say. If you have spinless bosons, which is over here, what would you get here for the spinless bosons? D sigma d omega is, of course, this thing squared, which would be f theta squared plus f pi minus theta squared. And then you would get the cross term, which would be f star theta, f pi minus theta, plus f theta, f star pi minus theta, which is equal to, f theta squared plus minus. This is plus twice the real part of f theta, f pi minus theta. So it's interesting. It's a different kind of interference term. It's twice this real part of this, and it's the opposite sign. And on the homework, you'll practice doing this kind of thing again. I think there you're considering spinless fermions, as I recall. In any case, you'll have some practice looking at this kind of thing. Any questions about that and what we did here? See, as soon as you include spin, it becomes more complicated because you have to consider all the combinations. But if you don't care about the combinations, then, well, you still have to calculate them because you still have to know what the spin space, the sort of irreducible representations of it that it breaks down into, like the triplet, the singlet, and so on. But once you have those, that's how you know what happens under particle exchange. That's how you know how you can construct this matrix here. You know that for each subspace corresponding to a fixed angular momentum for the spin space, a fixed spin, either the total thing is spin 0, spin 1, or other possibilities if you have more complicated spins. Once you have those, then you know what the amplitudes are because they have to be either symmetric or anti-symmetric, right? To ensure that the whole thing is either symmetric or anti-symmetric, if it's a fermion or a boson. This is for identical particle scattering. And then once you have this, to calculate a cross-section for like an unpolarized beam of these particles, well, you'll just sum over all the possible initial and final states, which you can rewrite as just a trace of a product of this scattering amplitude matrix thing. So that's how you can do it. And then, for a really unpolarized beam, the state operator is really easy. It's just the identity divided by, the dimension of your total spin space. So for 2 spin 1/2, it's 2 times 2, it's 4. For 2 spin 3/2, it would be 5 times 5, right, so on. All right, any questions about that? Before we move on to something quite different. Okay. So I'm going to clear this. So the next topic that we're going to talk about is called second quantization. And this is going to be the treatment of a large number of identical particles. So it's going to be a formalism to answer the question, what happens for a large n identical particles. And the idea is, for something like fermions, right? You wouldn't really want to do things the way we've been doing them because, well, it would be very annoying, right? If you'd want to write down the total wave function or something for like n fermions, you would, have to write this thing, which would be 1 over square root of n factorial times the determinant of some, n by n matrix of, the individual state wave functions. It would be a mess. It'd be a whole lot of terms. And so you don't want to develop things the way you would for, say, like 2 electrons or something, where you take antisymmetric combinations of the single particle wave functions. So that's where second quantization comes in. It's a way of thinking about these states in a different basis, you can say. And at this point, we'll sort of have a departure from the Bellac book. What the Bellac book does is largely just talk about some phenomenology of what happens when you have a large number of fermions and bosons. And you typically cover that kind of thing in a statistical mechanics course. But I guess we can say a little bit about it. So, and then when we actually deal with second quantization, the actual formalism, Bellac doesn't really cover that. So you can look at Sakurai or my notes or pick your favorite grad quantum book. It'll cover this typically. Bellac does not. He's some more interested in. I think he's an AMO physicist, so he's mostly concerned with small numbers of particles, and doesn't worry too much about second quantization because that's really more in the realm of condensed matter, right? Like, when would you have a large number of identical particles? Well, you would have it in, say, a piece of metal, where you'd have a whole lot of electrons in the metal. So it's sort of within the realm of condensed matter. So that's basically why Bellac doesn't really cover this very much, because he's more interested in doing the kind of single, maybe 2 particle Hilbert spaces. But anyway, that's sort of a tangent. But let's think about, one of the major applications of this formalism, which we'll see, would be n, identical fermions. You can think about electrons in a solid, maybe. And what's the idea? Well, the idea is each of those electrons will have a particular state. And what does that state consist of? Well, if it's just like a gas of electrons, and they're not interacting, they're just living out there. Well, a typical, a state of one of these things will be described by, well, it'll have some momentum, right? And it might have some spin, right? We spin up and down. And when you're dealing with a system of n of these guys, what will happen? Well, you need to be able to sum over all the possible states that these guys are in. And the idea is, remember that no two identical fermions can occupy the same state. So again, what will happen due to Pauli exclusion is that if you have n identical fermions, like in a gas, they'll start occupying all the different states, so different possible momenta and spin, starting with the lowest. So, it sort of depends on the temperature, of course, but the idea is that they'll want to go to the lowest possible energy state, but they can't all occupy that lowest energy state. So they'll start filling up these energies. And that includes for, a gas of them, where the only states are just different kinetic energies and different spin states. It'll start filling up those kinetic energy levels as well. So what will happen is, if you have a lot of them, the more you have, actually, the more states they get filled up, and actually the outermost states will actually be at quite a high energy, because if you have enough of those identical particles, they can't all occupy the small energy states. They'll fill them up, and so the largest occupied energy state can actually be quite large, and that's called the Fermi level. And you can actually kind of understand this by thinking about, these single particle states and thinking about summing over them. So what would you do? Of course, you would have to sum over what? Well, okay, so you have, what are your degrees of freedom? Well, in principle, you have the kinetic energy, you have the momenta. You also have the positions of the particle. They live in some volume. So you have to sum over those. And you also have the spin, the possible spin states. And so if you have spin S, then there's 2s plus 1 spin states. So that's the number of spin states. For electrons, of course, it's just 2. S is a half. So you have 2 possible things. And then you sum over all the possible momenta and positions of the particle. But of course, if they're not interacting, then, well, they all live in some volume, V, and X basically can take on any position inside that volume. But we know that you can't specify the position and momentum, right, precisely, and that there's a quantization of these, namely that the phase space breaks up into little boxes of size of Planck constant. There's and you can do this, of course, more formally, and we sort of did, when we derive the density of states. You can put the electrons in a box and sort of work all this out, and work out like the free particle wave functions and count them and do this sort of thing. But we're going to just kind of do it this hand wavy way for now, but it's sort of the same thing as it turns out. and doing it more formally, but I just wanted to show you some of this phenomenology. So is the sum. Okay, well, if, the sum over x will just give us a factor of the volume. And then, of course, we'll have to integrate over the possible momenta. And the number of little boxes that we can actually occupy that correspond to the different position and momentum states, those will all be of size h cubed, Planck constant cubed, because, in 3D. And so the volume of each of those boxes is 2 pi h bar. H bar, remember, is h over 2 pi cubed. So this is how you would do the sum over the different states of the say a gas of fermions. This is all the possible states you can have. And of course, to do this properly, you'd actually have to do the sort of free particle wave function counting business, but it's fine. We can do it this way. Sorry. This works also. And so if you wanted to, say, count the number of occupied states, then what would you do? Well, n, right? That's the total number of particles you have. And that's also has to be the number of unique states that are occupied, right? Including spin and stuff like that. That's Pauli exclusion. N has to be equal to 2s plus 1 v over 2 pi h bar cubed. So if you sum over the number of states, this is just the number of states, right? And the number of states you have is the number of particles because they all have to occupy their own state. So they can't, two of them can't occupy the same state. So however many states you have, that's how many particles you have for fermions. And so the total number of particles has to be equal to the sum. And the sum will go up to, assuming that you're at low temperature, everything wants to have the sort of smallest kinetic energy as possible. So it'll fill up all of the momenta up to some maximum amount, which we call the Fermi momentum, right? So it'll be an integral over all the momenta up to some maximum amount. And if we think about that, of course, the kinetic energy is just, p squared over 2m, the magnitude of the momentum vector. So what does this integral describe? It describes the volume of a sphere that's, goes out to size equal to the Fermi momentum, right? So this whole thing is 2s plus 1 v 2 pi h bar cubed. And this is the volume of a sphere. Out to size pf, which is the Fermi momentum. And so what does it mean? It means that we can actually solve for the Fermi momentum. We can figure out what it is as a function of the volume in which you put the particles and the number of the particles. So you can solve this for the Fermi momentum, and you'll get pf is equal to 6 pi squared, 2s plus 1, 1/3, h bar n over v, 1/3. Why am I showing you this? Well, because, see, it's interesting. The highest, the largest momentum of these particles is going to be proportional to the density of the particles raised to the 1/3 power. So it means that the denser you make the particles, the larger the kinetic energy is, right? And of course, this is also, associated with the Fermi energy, which is just, p squared, the kinetic energy associated with momentum, p squared over 2m. It's the largest kinetic energy of your occupied states. and you can just calculate what that is. And the point is it'll be proportional to n over v to the 2/3 power. And the scaling is actually quite interesting. But before we talk about the scaling, let's estimate what EF is for, say, some particles in a metal. So we can look at copper. And for copper, you would want to know what N over V is. And to do that, you would need to know the density of the copper atoms, and you would need to know how many electrons each atom contributes to conduction. So the idea is for a metal like copper, some of the electrons in the atoms won't be bound inside the atoms, but they'll be free to move around. And so they'll essentially be very weakly bound to their atoms, and they'll form a gas. And that's why conduction electrons in a solid can be well approximated as a gas of free electrons. And so in copper, each atom contributes approximately 1 electron to the conduction band. It contributes 1. It has each atom has 1 kind of electron that's loose enough to get out and run around. And so you can calculate N over V with that in mind. You just need the density of copper, right? And that tells you about the number of atoms per unit volume. So the density is 8.9 grams per cubic centimeter. You need to know what the weight is of a copper atom. And that's 63.5 AMUs. And you can do that to calculate what N over V is for the electrons that it contributes. And you can find that it's about 8.4 times 10 to the 28 electrons per cubic meter. Well, obviously a big number because everything is small. So we can do that and plug in N over V, and everything else just depends on H bar and stuff like that. And what you'll find is that the Fermi energy for copper is about 7 electron volts. And that is a huge number because, again, the most important scale for me anyway, and something worth remembering, is that KT, so the characteristic thermal energy at room temperature, is approximately 1/40th of an electron volt. So what does that mean? It means that in a typical solid like copper, the kinetic energy of the electrons is much, much larger than typical thermal energy. So that's why, from the point of view of those electrons, room temperature is actually very, very cold, right? It's much lower energy than the highest occupied states. So, yeah, and this is all sort of standard condensed matter stuff. I mean, you've probably seen it at some point, but I don't know. It's worth it to keep in mind the basic physics of why people go to second quantization, what it's used for. It's typically used to understand the behavior of things like electrons in a solid condensed matter applications. And the basic phenomenology of having a bunch of fermions is that they occupy a lot of states. They occupy so many states that, in like a solid, the occupied states have a very large kinetic energy just because there's so many electrons that they just fill up all your kinetic energy states, so that they actually have a very large kinetic energy. And that's very closely related to why, we experience objects as being solid. It's because the Pauli exclusion principle, it sort of gives systems of fermions kind of volume because they occupy so many states. It leads to a degeneracy pressure because, as you can see, even at very low temperatures, at zero temperature, the electrons will occupy states so that the kinetic energy is actually quite large, and that leads to things like chemistry and the solidity of objects and things like that. Pauli exclusion principle. All right. So another interesting thing we can look at is the actual energy, the total energy. So this is just the energy of the outermost occupied states. But of course, you can also calculate the total energy, which is just integrating up all those momenta. So the total energy is V pi squared h bar squared. It's just, if you do the angular integration, then it's just the integral of p squared over 2m, just the kinetic energy. And what you'll find is that this is 3/5 times n times the Fermi energy. Remember, Fermi energy is just the largest kinetic energy you have. This is the total energy. The total kinetic energy of your gas of particles. So you can calculate what sort of, energy per particle is. And this is where it gets kind of interesting, right? It'll be you sort of calculate what it is by, plugging in for the for the Fermi level. And what you'll find is that, the point is E over N, the average energy per particle, will be proportional to the density N over V raised to the 2/3 power. Same as the Fermi thing. Right? They'll just scale the same as the Fermi energy. And why is that weird? Well, it's because we can think about, for instance, so this would be the kinetic energy. What about something like the potential energy? What if, well, the electrons obviously have some Coulomb repulsion. We can think about the total potential energy, say, of electrons. And if we try to figure out what that is, say the Coulomb energy per particle, well, this thing would be, what would it be? Well, there's n particles, and each one, they're sort of going to interact with a potential E squared over R, where R is the separation between the electrons, and the separation must be just the density N over V, right, raised to the minus 1/3 power. That'll give us a length scale corresponding to that density, right? Or if you want, it's the cubic root of the volume per particle, right? That just gives us the average distance between the particles. And of course, per particle, this will have the scaling N over V raised to the 1/3. So this is very weird because it means that as you make the gas denser, you would think that makes the Coulombic part win out, but actually as you make the density larger, it's the kinetic energy that wins out. It's the Pauli exclusion principle that wins out as you make it denser. And so that means that as you make the gas of electrons, say, denser, it's actually becomes more of an ideal gas, meaning that you can ignore like the Coulombic interactions between the electrons, because it's all of the phenomenology will be driven by the Pauli exclusion principle and the kinetic energy. So that's interesting and I think counterintuitive and sort of strange. Bosons are kind of the opposite. So if you have a gas of them, then they can all just go to the quantum mechanical ground state at low energies. And that yields the phenomenon of Bose-Einstein condensation. Probably heard of that. And we won't really talk about that, but I mean, basic idea is pretty clear. There's no Pauli exclusion principle, so the bosons can occupy whatever states they want. So in particular, at very cold temperatures, they can all fall into a single quantum state, which is one way in which you can observe quantum mechanical properties on the macro scale, right? Because you can have a macroscopic number of particles all in the same single quantum state. That's what makes Bose-Einstein condensation interesting. But the point is, this is all phenomenology. So sort of hand-wavy scaling arguments. We want to actually be able to do the quantum mechanics of an arbitrary number of particles, and that is why you want to move to second quantization formalism. So that's. But any questions about this hand-wavy stuff? It's just nice conceptual stuff, I guess. Presumably you've seen it before at some point. Okay, so in the last 2 minutes here, we're gonna talk about, actually second quantization. And the idea is, instead of writing out the complicated wave function of symmetric and anti-symmetric combinations of the single particle wave functions, what you do is you think about occupation numbers instead. And what you say is you just specify how many particles you have in each single particle state. So you say, I have n sub I particles in state I. And so then your multi-particle state is written as just the set of occupation numbers for each possible single particle state. And typically there's an infinite number of them. So that's the kind of the disadvantage. If you only had 2 particles, you can just sort of say which state they're in, write down the symmetric or anti-symmetric combination and be done with it. But once you move to this occupation number representation, well, then your states will look like this. You have to actually tell me what the occupation numbers are for each possible single particle state. And a lot of these are going to be 0. A lot of times you'll have no particles in that state. So, that's the price you pay in a sense. Is that you kind of have to specify all the unoccupied ones as well, but you list them all for all the different states. So if you had, say, particles living in a box, well, you can see already that that's sort of a problem, because in principle there's like there's an infinite number of single particle states that you can be in, and so you'd have to just include all those and just put zeros for all the unoccupied ones. But we live with that. The advantage of this is that you no longer have to worry about symmetrizing or anti-symmetrizing because it's sort of automatically incorporated in the formalism, as we'll see. And I guess that's time, but that's a good place to stop. And next time I will develop this and see how you actually use it, how you can construct like a Hamiltonian using this as a basis for your states, and so on. It's a different representation of, multi-particle states. Instead of using tensor products and things like that, you just tell me how many particles you have in each single particle state. And this only works for identical particles, obviously, because otherwise this wouldn't be a unique representation, right? If I tell you that there's 3 particles in state 5, then well, if they're distinguishable in some other way, then that's not enough. You have to tell me, which 5 particles are in state 5 or what have you. So it's for identical particles.